All right, let's explore a little bit more about the concept of a vector. Now that we have grade 11 under our belts, we know that a vector has basically two components. It has a magnitude, and of course it has a direction quality to it. So it conveys two different bits of information at the same time. And so, you know, if you were to walk 6 meters, that's a distance that you've walked. But if I say go 6 meters, you might stop and look at me funny because I'm leaving out an important part of the information. What if I said, well, walk 6 meters west? Then it would make more sense. You'd know which way to go. So we can describe things like this without a direction, which we call scalars. But when we add a directional component, it's now called a vector. And a vector is really just a version of an even more complex kind of mathematical construct called a tensor. But we won't get into that because that's for university level. So right now, what we're looking at is vectors, but I want to talk about how we describe them mathematically. We want to learn a little bit more math language to help us out when we move into next year, when we start studying vectors in university programs where they're a little more complex. Okay, so the easiest way to represent a vector is with an arrow. So let me take an arrow and let me draw it here like this. If I measure this arrow, I might measure that, you know, it's 5 meters long. And I can sort of see by the arrowhead which way it's pointing. So I have no trouble knowing which way the vector is actually going. Now, I can also add a number to that. Maybe I want to find, oh, I have to just double check that my sound is working here. There we go, because it made a funny noise. Okay, we want to know, for instance, which way this is going more specifically than sort of, you know, the direction it's pointed. We could describe that direction by using an angle. So what we could do is we could set up a sort of an axis system here, a reference point or a reference frame. Remember we talked about reference frames. And we could measure this angle right here. And I don't know, maybe it's going to be 30 degrees or 45 degrees or whatever that could be. The angle, we'll call it the angle theta for now. And that angle could tell us which way to point. Because in a two-dimensional reference frame, on this entire graph that I've drawn, there's a different angle for every possible direction that you could go. Okay. Now, so let's think about what we learned in grade 11 was that we could also take this vector and we could use this little reference frame that I've put on it, and we could describe the vector in two ways. We could describe the lefty-righty motion of the vector, what we call the x component or the horizontal component, and we could also then describe the vertical component of the vector. And if you look at this vector triangle, you'll remember the rule of adding vectors is tip to tail. So the blue arrows, you'll notice, are oriented tip to tail. The tail of one is touching the tip of the other. And they start and end with the black arrow. They start at the start of the black arrow and they finish at the end of the black arrow. So what that means is that the two blue arrows add together to make the black arrow. If you move in these two blue directions at the same time, you will trace out the black arrow, right? So we could call this side 5, and the way you get this is by taking some trigonometry, 5 sine theta, and this side is 5 cos theta, whatever the angle is, and we call these the components of that vector. Okay, so let's imagine a triangle where we've done this. Let's draw another one here. I'll put in another axis here. And let's take, whoops, a triangle that's quite common. Let's take the 3, 4, 5 triangle, the right angle triangle. So let's say that this is a 3, this is a 4, and this is a 5. Now, we can figure out the angle then by using some trigonometry. We could take the 3 divided by the 4 and then do the tan, which is about 36.8 degrees, 36-ish, 37 or so. Well, let's round it off and say it's around 37 degrees right here. Right, and I did that by going tan theta equals 3 over 4, opposite over adjacent. So theta works out to 37 degrees. All right, so we have that. Now, in mathematical language, we actually use these components quite often. There's a couple of ways we can mathematically describe this vector. The blue arrows stand for the x and y components. So what we could do is we could draw the graph like this and realize that the graph must go from the point 0, 0 at the origin, but it must go up 3 and over 4. So this point at where it finishes must have an x value of 4 and a y value of 3. So we can describe the vector as an ordered pair 4, 3, as long as we understand that the original point of the vector always starts at the origin. Right? It makes sense, it's the origin. So that could be the vector 4, 3. Another vector, say this one over here, well, that could be a vector that is negative 4 and perhaps that looks like about 5. Whatever the ordered pair would be right here at the end of the vector. So vectors can be described with ordered pairs with the understanding that the tail is on the origin. And that's a simple way to describe vectors. Now, another way to do that is with an interesting kind of language. What we do in math is we say, okay, let's take those blue arrows again, the 3 and the 4. Let's say we don't want to use the ordered pair idea, so let me erase that. Well, if you wanted to measure something, you have to have a unit with which to measure it. So if I was going to measure the blue line with meters, I would line up my little, oh, rats. I think I can undo that. I would line up my little meters, my little meter sticks. One, right there's 1 meter stick, and then another meter stick, 2, and then another meter stick. And of course, they should have all been the same length, but you get the idea. I would need 4 meter sticks, right? Now this could, maybe it's not meter sticks. Maybe that 4 represents 4 kilometers. So each of those little green, little standard things, those must be kilometers. So what we do is we give a name in math for those little standard measuring sticks. Those little measuring sticks, whatever they may represent, are called unit vectors. We call them the unit vector because that just means the vector equal to 1, right? 1 meter, 1 centimeter. They could be any length. They can be anything, but they are always 1 unit. And then you just measure them up. And so what we do for the one on the x-axis, we call it I. So I is the x-axis unit vector. So that means, very simply, that the line we have drawn, the original blue line right here, that was 4 of those units. And so we say that was 4i. It's just a fancy way of saying that we want to move 4 along the x-axis, 4 of whatever our units are. And then by the same token, we can measure the 3 going up in the same way. Well, the 3 going up, again, would have little unit vectors like this, whatever they were. There'd be 3 of them. And so we call J the y-axis unit vector. That's what you're measuring the y-axis with. Whatever it is, it's 1 of something. It's 1 kilometer, 1 centimeter, 1 1 decimeter, whatever that might be if you're measuring displacement. And so in our case, it would be 3 of those little sticks, and we would say that would be 3J. We could add yet another 3-dimensional sort of z-axis that would come in and out of the board. And I could also have measurements on the z-axis. We won't do that because it's a little complicated, but guess what? K is the z-axis unit vector. So you could also add a 3rd dimension to your vectors. We're not going to do it for our sake, but down the road you might. Now, what are we doing with those 2 blue vectors? Let me draw them again. You'll notice they're right back up here. They are positioned tip to tail, which means they are being added. In order to get the black arrow properly, you have to add the 2 blue 3 and 4 vectors. So if this is the one of the blue along the x and this is the blue along the y, then we would write 4I plus 3j. And that essentially means 4 units along the x-axis plus 3 units along the y-axis. And so you could imagine if you took a little walk along this little line, you would go 1, 2, 3, 4 along the x, 1, 2, 3 along the y, and you would end up at the end spot. And that's the equivalent. It's the equivalent of moving along this black line in this direction like this, which is now red. And so that's how we can represent that vector. Well, how do I get rid of this? Nope. Like that. There, sorry about that. Okay, so that's how we can describe this vector. We can call it 5 at 37 degrees. We could call it, let me show you all the different ways then. We could call it 5 at 37 degrees as our sort of, that's the way we would have done it last year in grade 11. We could use the ordered pair of 4, 3 to describe it if we accept that the tail is on the origin. Or we could describe it as 4 steps in the x direction plus 3 steps in the y direction. And of course, if you had a 3-dimensional vector, you could add here whatever it would be, 2 or 5 in the k direction if you wanted to. So that's a 3-dimensional vector, but that's for a little bit later on. We'll just handle 2 for now. And so you're going to start using this notation, whoops, you're going to start using that notation in your university years right here very, very soon. So it's a good idea to get the hang of it. You might even use that a little bit in your calculus or algebra vectors, calculus and vectors, and so on. Now, what's interesting is there are now a whole bunch of rules you will learn on how you can add vectors together by adding up all their components. So you'll remember last year, we did an exercise where we took a bunch of forces like this. One force went this way, one force went that way, another force went this way, and so on. And we called them A, B, and C. And we had to figure out what the net force was. So what we did is we added up their components. We took the components of A, the components of B, and the components of C, whatever those were, and we added them up. We added all the AX's, BX's, CX's with all the Y's, the AY's and the BY's and the CY's. Well, the blue vector here of A is just some number of I. Let's call it maybe it's well, I won't even put a number there because it'll just mess us up. It's some movement of I along the x-axis plus some amount of j, right? Those are our unit vectors. Let's say it was 2 and 3, just for fun. And then let's say this one down here, if you look at the green one, if you look at vector C, it looks like it's going down and over. So it's got a negative, let's say -2 for the x component on the bottom, plus what looks like also a negative on the y. So that would be maybe you're adding a -6j. which we would write as negative 2i minus 6j, right? We would combine those two to make a minus. And then over here on the red, let's say the x looks like about a negative 3 and maybe a plus 4. So negative 3i plus 4j. And those are the components. So if we add up all the i's, if I write these vectors underneath each other, 2i plus 3j, and then I go down here and I write this vector here, negative 2i plus 6j, if I add up all the i's and all the j's, oh, that's a negative, my mistake, sorry. That's a minus 6j there, got to watch that. Well, what I have here is I have 4 plus 3 minus 6, which is 1. So I end up with just 1 j left over. And then I have over here a negative 3 and a 2 and a minus 2. Well, that's a minus 3i. And so this represents then the vector that I would have as the overall sum of those two. And I could get that vector by drawing my graph again and going negative 3 on the x and up 1i. So this is the overall net force. So you see there's rules that we will learn, you will learn as you learn to use this notation. But I thought I would introduce it to you because it's very, very closely related to what we do when we say the x and y components. And it's an interesting way of showing those components. And I know that in universities, they use that quite often. And so it's a good idea to sort of been introduced to it, at least a little bit, if you haven't already. Okay, so that's some of the ways that we can mathematically represent vectors, and then we can learn how to manipulate them. We can add them in this way by adding all their components. There are ways we can multiply vectors, and you'll learn all these rules in your calculus class, calculus and vectors actually, and then you will learn the rest of them as you go. We won't be needing too many of them. We'll be able to do things sort of similar to how we did them last year without getting too crazy. But a little bit of mathematics for the people who want to get a jump on dealing with these things. And we'll stop that there.